This is my fourth video in my module on linear programming, which we're going to work through an actual example of when we would use this, okay? And so it's kind of a hypothetical with prettier numbers just to kind of get through it, but yeah, this is how we would use a linear programming type of method to solve for maximizing profits, say, which is what we're going to do here. So let's go ahead and get started. We say write a system of linear inequalities that represents the constraints for the following scenario, okay? We also want to write an objective function that represents our profit in this case. And then we're going to use the graph of that feasible region to find a value that's going to perhaps maximize our profit equation or our objective function. So in this case, our objective or our goal is our profit. And we want to maximize it, okay, subject to certain stipulations or constraints, okay? So here's what we have. We say a candy manufacturer wants to maximize the profit for two types of boxed chocolates. So we have two types of chocolates. Kind of a key thing to pay attention to here. A box of chocolate covered creams yields a profit of $1.50 a box, and a box of chocolate covered nuts yields a profit of $2 a box. So those seem pretty important to us here. Market tests and available resources have indicated the following constraints. Okay, so here's what we have here. These are actually our constraints down here. What we've just read over is actually our objective function here. We're talking about profit. So we're going to start with this profit equation. When we talk about profit, you know, we've been using z to represent the objective function. In this case, we say our objective function. What we're going to do is we're going to say this refers to profit. So we'll say p. And in order to calculate profit, if one thinks about it, you know, we're getting $1.50 a box for the creams and $2 a box for chocolate covered nuts. So we could calculate our profit as saying $1.50 times however many boxes of the creams we sell and $2 times however many boxes of the nuts we sell. So perhaps even before we write our objective function, we should start by defining our variables. Let's let x equal number of boxes of the creams. Okay, so number of boxes of the creams. We'll let y equal the number of boxes of the nuts. Chocolate covered nuts. Nuts, man. So anyways, we say we have this here. So our profit would be this. Well, we earn $1.50 times however many boxes of this we sell. Pardon me for not writing 1.50, but 1.5 times that plus $2 times this. This would basically be how we would calculate our profit, I mean, if you were running this business. So now what we're going to do is we're going to develop some constraints. Now, important that we start by defining the variables because all of these are kind of hard to wrap your head around at first. But once we kind of set up the fact that x is the number of boxes of creams and y number of boxes of nuts, we can actually work our way through this and writing an algebraic sentence to represent what we have as a word sentence. So we say, number one, apparently market research shows that the combined production level should not exceed 1,200 boxes per month. Now, when you're solving linear systems, not systems of linear inequalities, in the past we say, you know, maybe the combined production is exactly 1,200 boxes per month, which would be like, you know, x, which is the number of boxes of creams plus the number of boxes of nuts y would equal 1,200. In this case, we say it should not exceed, okay, not exceed 1,200 boxes per month. So what we're really saying here is this. The number of boxes we sell here of these plus the number of boxes we sell of these should be less than or equal to 1,200 boxes total. Okay, so this is what makes this kind of a linear programming instance, is the fact that we have a constraint, not just exactly equal to 1,200, but less than or equal to. Number two, it says the demand for a box of chocolate covered nuts is no more than half the demand for a box of chocolate covered cream. So let's break this down, what this says here. We say the demand for a box of chocolate covered nuts. Okay, so chocolate covered nuts, we're kind of like saying that was our y, is no more than. When we say no more than, we're kind of mean less than or equal to half of, which means 1/2 times the demand for a box of chocolate covered creams. So we say that would be x. So in this instance, we come up with this constraint here. We say y is less than or equal to 1/2 x. Cool. All right. So we say the next constraint, the production level for chocolate covered creams. So this here would be chocolate covered creams. We're saying this is like our x. Should be less than or equal to, so of course that kind of says what it means, less than or equal to 600 boxes plus 3 times the production level for chocolate covered nuts. So less than or equal to 600 boxes, so that'd be 600, plus 3 times the production level for chocolate covered nuts. So we say 600 plus 3 times, not 300, but 3 times the production level of the nuts, which are our y value here. So we get this, we get x is less than or equal to 600 plus 3y. So here are our constraints. There are actually two constraints that we do need to consider. In this instance, we say we're not going to sell negative boxes. So when you're working with linear programming, often with real life situations, we include these two constraints here. Here's what we need to do. We need to graph this feasible region associated with these constraints. And then what we'll do is we'll find the vertices and find out which one would maximize our profit. So let's go ahead and start with this. This here, if we were to graph it, it has intercepts at 1200, try saying, comma 0 and 0 comma 1200. So we're going to have to be creative with our scale here. This one down here, I mean, if we were to say bring the x back over to this side, it would be negative 1/2 x plus y is less than or equal to 0. Another way to write this. But it would have an x-intercept of 0, y-intercept of 0. We actually can't get away with using intercepts on this one. We have to say it has a y-intercept of 0 and a slope of 1/2. So we're going to leave this in slope-intercept form. Coming down here, if we were to maybe drop our 3y back over here, we get this. We'd say x minus 3y is less than or equal to 600. We can develop some intercepts off of this. For example, we would say our x-intercept is 600. Y is 0. We say if we were to plug in 0 for x and solve for y, we could say, all right, well, solving for y in this instance, when x is 0, we get negative 200. Negative 200. Whoops. We already plugged in 0 for y, got an x value of 600. If we plug in 0 for x, pardon me, we get a y-intercept of negative 200. Okay, and then last but not least, down here on these two, we'd say, well, I know what those look like. These are these vertical lines here. So we're going to go ahead and graph in our constraints. I'm going to do so rather quickly here. We say, here's x equals 0. Here is y equals 0. So we say y equals 0. And x equals 0. Here are these two constraints, okay? Working with the other ones here, we say, well, 1200, man, that's rather large. We should probably go by hundreds here. So we say like 1, 2, 3, 4, 500. We only need to label like every 5 here, 3, 4. Here would be 1,000. 1, 2, 3, 4, and 1,500. Okay. Same thing over here. We say like here's 500, here's 1,000, here's 1,500. So 500, 1,000, 1,500. So let's go ahead and drop in this first constraint here. We say it hits it, 1,200 and 1,200 on these. So very, very carefully, I'm going to drop in this constraint with a solid line. It was an or equal to type of situation. And we say this is the equation x. Let's put this in a different color. X plus y equals 1,200. Now our next one here, we said, well, we'd have to graph it in slope-intercept. We know it has an intercept of 0, but because it has a slope of 1/2, just because, we'd say, all right, up 1 over 2 doesn't mean we can't go up 100 over 200. It would have this kind of scheme right here, up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, and we just keep doing this. And it is also a solid line. So you get this guy here, and its constraint was this, y equals 1/2 x, okay? And so we have this last constraint here. We said it has an x-intercept of 600. So we'll go over to 600, draw a dot. Now since my y-intercept down here is down here at negative 200, I could try to say, well, negative 200 is about right here. But I could also say this, well, if I were to put it in slope-intercept form, that's this guy here, we say, it would look like this. We'd say 3y greater than or equal to x minus 600. And dividing everything by 3, we get greater than or equal to 1/3 x minus 200. So here's our negative 200 on our y-intercept, but it goes up 1 over 3. So we say up 1, right 3. Up 1, right 3. Up 1, right 3. So here's this guy right here. So got to know how to graph things. So we say x is less than or equal to 600 plus 3y. Okay, cool. So since we have this set of constraints here, we can go ahead and test them all. You'll notice that we can test 0, 0 on all of these except for this one right here because it goes through 0, 0. So we're going to have to test a different point on that one. But saying the ones that we can test 0, 0 on, and to be these two oblique constraints here. Oops, this one here and this one here. If we were to test 0, 0 on the first one, we get 0 is less than or equal to 1,200, which is a true statement. So that was this constraint here. It's going to shade downward. This is the one where we said we can't produce more than 1,200 boxes combined, okay? And then our next constraint we could test 0, 0 on, which is this x is, we'd say plug in 0 for x, we get 0 is less than or equal to 600 plus 3 times 0. So in other words, 0 is less than or equal to 600, and that's true. So we get this shading towards 0, 0. So this is going to shade up here. Up, up, up toward the side containing 0, 0. We also know this, x greater than or equal to 0 means we're going to shade this way, for instance, and y greater than or equal to 0 means we're going to shade this way. Boom. Okay, so the one we actually have to test a different point on, this y is less than or equal to 1/2 x. We can't test 0, 0 because it's on the constraint, but we could test something like this point here, which would be 100, 0. So in other words, we say 100, 0. If I'm going to test this with this constraint right here, then we would get this. We'd say, well, plugging in 0 for x and 100 for y, we get 100 on the left is less than or equal to 1/2 of 0. Is 100 less than or equal to 0? No, this is false, okay? So we'd say we would shade away from this side. We'd say, really, what we end up with is this feasible region where these all shade together. And so what we're seeing is this feasible region. Let me get a darker color here. Right here. This is kind of the outline of the feasible region. Right here, where everybody was shading together. So now the question is, well, which of these points in our feasible region would actually maximize our profit? Well, it would have to lie at a vertex. And we have 3 vertices on this. And the nice thing is, we actually know 2 of the vertices right off the bat. I mean, we knew this was the point 0, 1200. And we know down here that this is the point 0, 0. I'm guessing to produce 0 of each box is not going to maximize our profit. But this one right here, we're actually going to need to solve for. And the good news is we have both of the constraints in the system here. We knew that y equals 1/2 x is one of its constraints. We have x plus y equals 1200. So if we were to do, say, substitution method here and plug this in, we get x plus 1/2 x equals 1200, which means 3/2 x equals 1200. And multiplying both sides times the reciprocal, which is 2/3, 2/3. We say 1/3 of 1200 is 400. We could cross cancel these. This becomes 400. And then 400 times 2 is 800. So we get x equals 800. And if x equals 800, we'll plug this back in right here. We get y equals 1/2 of 800. We get y equals 400. Okay. So we have this vertex here as well. We say this is the point x equals 800, y equals 400. So now we can create our optimization table here where we're dropping in our vertices and our objective function, which in this case was profit, is 1.5 times the number of this many boxes and $2 times this many boxes here. So we say here are vertices 0, 0. We had the point 0, 1200. We had the point 800, 400. And so maybe we pull out our calculator here and get these rock. And I know this on the first one here, we say 0 into both of x and y would produce a profit of 0. Of course, producing neither of each type of box of chocolates would produce no profit. But in this case, we say 0 in for x would be 1.5 times x, which is 0 in this case, so that'd be 0. And then 1200 times 2, not when I need my calculator here, we say this would be $2,400 profit. And then we say, okay, well, what if I wanted to do this last one? We say 800 times x, which is 1.5 in this case. That'd be 1200 plus 400 times 2, which is 800. So we could add on another 800 here. We get $2,000 profit. So here's the deal. We wanted to maximize our profit. So essentially what we want to do with this is this. According to our market research, if all of these things are true, what we're going to want to do is this. We will want to produce this. Now we define y to be the number of boxes of chocolate covered nuts and x to be the number of boxes of creams. Produce no creams. So of course I made this up. And 1,200 boxes of nuts, chocolate covered nuts. And this would give us a max profit of $1,200. Sorry, not $1,200. $2,400 that we see right here. So this is just kind of a real quick run through of how you apply linear programming processes. Cheers.